Hello there. I'm glad you've slipped into this little pocket of quiet with me. Outside, the universe is carrying on, as it always has, stars burning in silence, galaxies turning like slow wheels in the dark. Yet tonight, we'll linger on a subtle change in how we see it all. Over the years, astronomers have learned to listen to the cosmos in many different ways, with light, with gravity, with particles that barely touch anything at all. Recently, a new kind of hearing has joined the mix, like discovering a soft harmony beneath a song you thought you already knew. It doesn't make the old universe vanish. It adds another layer to it, a hidden pattern unfolding just beneath the familiar glow of the night sky. If this gentle kind of wondering feels like a good place to rest your thoughts, a quiet like and a soft subscribe, help others find their way here too, only if it feels right. Tonight, we'll wander slowly into that new layer together. On a quiet day in early September of 2015, our planet was going about its usual business. Clouds formed and faded, traffic lights changed from red to green, people made coffee and checked their phones. And far away from all that ordinary motion, deep in the darkness between galaxies, two invisible giants had already finished a violent dance. Long before anyone on Earth noticed, they had spiraled together, collided, and fused into one heavier black hole, shaking the fabric of the universe as they did so. On September 14th, 2015, some of those tremors finally brushed past Earth. They did not sound like thunder or look like lightning. They slipped through the planet, through mountains and oceans and cities, stretching and squeezing space itself by an amount so tiny that no human sense could ever feel it. But out in the quiet of the countryside, at a place called the Laser Interferometer Gravitational Wave Observatory, LIGO for short, something was listening with a kind of patience that had never existed before. There, a faint signal appeared in the data, the first direct detection of gravitational waves. It was the confirmation of a century-old prediction, and in 2017, it would be honored with the Nobel Prize in Physics. But even that medal is a small symbol compared to what really happened that day. The universe revealed a new way of speaking to us. One way to feel the importance of this is to imagine a different version of our species. Picture humans who evolved exactly as we are now, with thoughts and language and curiosity, but without the ability to see light. No colors, no sunrise, no stars. For thousands of years, they would move through the world using touch and sound and smell, building tools, telling stories, learning patterns in the dark. They might know that objects exist, that there are seasons, that something warms them in the daytime and cools them at night. But the sky would be a mystery, felt only on the skin. Then, one day, someone invents a machine that can see light for them, a device that takes the invisible waves washing over their faces and turns them into something they can understand. At first, the images might be blurry and hard to interpret, strange shapes and glows. But with patience, those shapes would sharpen into trees and mountains, clouds and oceans, the sun and the moon. In time, their machine would show them other worlds circling distant stars, and finally the faint smudge of entire galaxies drifting in the deep. It would not just answer old questions, it would raise new ones they never knew to ask. That is the scale of what LIGO gives us. It is more than a test of whether Einstein was right. It is the opening of another sense. Until now, we have seen the universe, mainly through light, radio waves and X-rays, visible colors and infrared glow. Photons have been our main messengers, bringing news from stars and galaxies. From hot gas and cold dust, gravitational waves are something different. They are ripples in space-time itself, traveling at the speed of light, carrying information not from the glowing surfaces of objects, but from their deepest, most violent motions. These ripples are everywhere, passing through us all the time, but they are incredibly faint by the time they reach us. To notice them, scientists built instruments among the most sensitive ever created. In long, L-shaped tunnels, lasers travel back and forth along vacuum tubes, bouncing between mirrors that must hardly move at all. If the distance between those mirrors changes by a fraction of the width of a proton, the pattern of the laser light shifts. That is the kind of whisper LIGO is built to hear. When a wave passes, space along one arm of the L stretches slightly, while the other shrinks. Then they trade roles, and in that tiny dance, the signal appears. Every time such a signal is captured, it is a tremor from a far-off drama. Two black holes colliding, the core of a massive star collapsing in a supernova. Perhaps even stranger events we have not fully imagined yet. The wave carries clues about what happened, how massive the objects were, how fast they moved, how far away the event took place, and when it occurred in cosmic history. Learning to read these clues is like learning to understand a new language murmured through space. To see where these waves come from, it helps to rest for a moment with the idea of space-time itself. In everyday life, we talk about space and time as if they were separate things. You move across a room, and you wait an hour for a friend. Einstein invited us to imagine them woven together instead as one four-dimensional fabric, 3 directions for moving around, and 1 for moving forward in moments. Every object with mass, every planet, star, and galaxy presses into that fabric and curves it. A common picture is to imagine a stretchy sheet held taut and smooth, like a trampoline or a soft drum skin. Place a small pool ball on it, and the cloth bends a little. Place a heavy bowling ball, and the dip becomes deeper and wider. In this image, the balls are like objects with mass, and the shape of the dip is like the curvature of space-time. Smaller objects roll along paths determined by that curvature, which we experience as gravity. Near Earth, that path looks like an orbit. Near a star, it might curve more sharply. Near a black hole, it could bend so much that not even light can climb out. Now imagine those massive objects not sitting still on the sheet, but moving. As they drift or orbit, the shape of the dip in the fabric shifts with them. When the masses are modest and the motions gentle, the fabric adjusts quietly, almost as if nothing special is happening. But when the objects are extremely heavy and their dance becomes frantic, 2 black holes spiraling together, for example, the changing curvature sends ripples outward. The fabric does not just sag, it shivers. Those shivers, moving away at the speed of light, are what we call gravitational waves. They spread in all directions, a bit like the circular ripples that expand when you drop a stone into a still pond. Only here, the water is space-time itself, and the stone might be the collapse of a star or the merging of dense remnants. As the ripples travel farther from the source, they grow weaker and wider. By the time they wash through our part of the universe, the change they bring is vanishingly small. If you had 2 objects floating a distance apart and a gravitational wave passed through them, the space between them would stretch and squeeze slightly, one moment a tiny bit larger, the next a tiny bit smaller without any force pushing them in the usual sense. It is a strange thing to picture, the rulers themselves expanding and contracting, the background of reality breathing around the objects it contains. Einstein's equations whispered that such waves should exist. But when he worked through the numbers, he doubted that anyone would ever be able to measure them. The amount of stretching and squeezing seemed too tiny, too shy, to ever stand out from all the other motions and noises of the world. And it is true that what LIGO looks for is astonishingly small. Many of the changes in distance it measures are on the order of a 10,000th of the diameter of a proton, an almost absurdly delicate shift. Imagine trying to detect a change in the distance between Earth and the nearest star beyond the Sun that is smaller than the width of a human hair. That is the kind of precision required. Yet hidden in those faint distortions is a wealth of information. The exact shape of the wave, how quickly it rises, how long it rings, how it fades, acts like a signature. From it, scientists can tell whether the source was a pair of black holes, a pair of neutron stars, or some other configuration. They can estimate the masses involved, the distance to the event, and even how fast the universe has been expanding while the wave traveled to us. Each detection is not just a yes or no, but a detailed postcard from a distant, often invisible corner of the cosmos. To catch these postcards, LIGO relies on more than one ear. It is not a single observatory, but two twin facilities in the United States, funded by the National Science Foundation and operated by teams at MIT, Caltech, and many partner institutions. One observatory stands in the desert of eastern Washington state, near a place called Hanford. The other lies in the countryside of Louisiana, near Livingston. Each site has two long arms at right angles to each other, forming a giant L traced out on the ground. In each arm, laser light travels down a vacuum tube 4 kilometers long, reflects off mirrors, and returns to the central building, where the beams are reunited and compared. When a gravitational wave passes one of these observatories, it ever so slightly changes the lengths of the arms in different ways. Because the two facilities are separated by thousands of kilometers, a wave will wash over one a tiny fraction of a second before it reaches the other. By comparing those signals, scientists can check that they are seeing the same cosmic event rather than a local tremor or a passing truck. As more detectors join in around the world, that comparison becomes even richer. With 3 or 4 ears listening together, it's possible to triangulate where on the sky the wave came from, to guide telescopes toward that patch of darkness, and to watch the universe answer in both light and gravity. All of this, the sensitive mirrors, the quiet tunnels, the instruments holding their breath, exists so that we can hear what was once only a mathematical whisper, turning Einstein's cautious prediction into a steady, ongoing conversation with the cosmos. Behind those long tunnels of laser light, though, are people who spent much of their lives turning that whisper into something we could finally listen to. Physicists like Kip Thorne, Rainer Weiss, and Barry Barish, often spoken of together, like companions on the same long road, helped carry LIGO from rough sketches and tabletop experiments to an observatory delicate enough to feel the faintest shiver in spacetime. Around them, engineers, technicians, students, and countless collaborators added their own pieces, polishing mirrors, quieting vibrations, refining code. When the first signal was confirmed and the faint chirp of merging black holes rose from the noise, it was this whole patient effort that the Nobel Committee chose to honor in 2017, not just the moment of detection, but the decades of work it took to build a machine gentle enough and stubborn enough to hear the universe move. At its heart, LIGO is a kind of interferometer, an old idea made extraordinarily large and quiet. Long before gravitational waves were detected, physicists had learned that you can uncover hidden details simply by letting beams of light overlap and watching how they behave together. The word may sound heavy, but the principle is gentle. An interferometer pays close attention to what happens when waves meet. Think of a small pond at dusk, its surface calm. Drop one pebble and you see rings spreading outward, evenly spaced. Drop a second pebble nearby, and its rings spread too. Where the ripples cross, they do something interesting. In some spots, the peaks line up with peaks, raising the surface a little higher. In others, a peak meets a dip, and they partly cancel, leaving the water flatter than you would expect. The pattern that appears is simply the way waves share space. Light behaves as a wave as well. It has a rhythm, a pattern of peaks and troughs that can either match or misalign with the rhythm of another beam. If two light waves arrive perfectly in step crest with crest, trough with trough, they reinforce one another and appear brighter. If they arrive half a step out of sync, one crest falls where the other has a trough, and they dim or cancel. An interferometer brings beams of light together and watches how bright or dark they become at certain points. From those changes, it can tell how in step the waves are, and from that, how far each has traveled or what it has passed through. Even tiny mismatches in distance or speed produce measurable shifts in the pattern. The larger and more carefully built the interferometer, the more subtle the differences it can reveal. LIGO takes this principle and stretches it over kilometers. Each of its two observatories, one in Hanford, Washington, and the other in Livingston, Louisiana, is shaped like a giant letter L laid gently on the land. From a central building, two long arms extend at right angles, each about 4 kilometers in length. Having two such observatories far apart is essential. A gravitational wave traveling across Earth reaches one a fraction of a second before the other. By comparing that tiny delay and the shape of the signals, scientists can begin to work out where on the sky the wave came from, the way your two ears help you locate the source of a sound in the dark. Inside each central building, a powerful laser serves as the light source. Its beam is steady and intense, with a power of hundreds of thousands of watts, handled with great care because it would be dangerous to anything in its path. This beam is sent toward a beam splitter, a small block of transparent material set at a 45-degree angle. When the laser hits it, the single beam divides in two, one half sent down one arm of the L, the other half sent down the other. In that simple act, one line of light becomes a pair of twins, identical at birth, but about to take different journeys. The arms themselves are long vacuum tunnels, steel pipes emptied of almost all their air. Pumps work to reduce the pressure inside to a tiny fraction of Earth's atmosphere, far lower than what you would feel even at the edge of space. This near emptiness is important. Molecules of gas drifting through the beam could scatter the light or push very gently on a mirror, adding noise to a measurement that depends on extraordinary stillness. By making the arms so empty, the builders of LIGO let the light travel with as few interruptions as possible. At the far end of each arm waits a mirror, polished and heavy. When the light reaches it, it does not reflect once and return. Instead, the beam bounces back and forth between this end mirror and an inner mirror nearer the beam splitter, making the trip hundreds of times. Each bounce keeps the light inside the arm a little longer, effectively stretching its path from 4 kilometers to a length many times greater. It is as if the beam is walking the same hallway again and again. With roughly 300 such trips, the effective path grows from a few kilometers to more than 1,000. This long journey makes the instrument far more sensitive, because a tiny stretch in the arm length has more time to change the light's rhythm. After all of these back and forth travels, the two beams return to the beam splitter and are recombined. They then head together toward a photodiode, a small, quiet piece of electronics that plays the role of an eye, able to register even a faint trace of light. LIGO is tuned so that, when space-time around it is undisturbed, the beams reach the photodiode almost perfectly out of phase. Their peaks and troughs are arranged to cancel. In that calm state, barely any light arrives. The detector sits in a kind of artificial darkness, created not by the absence of light, but by the precise way the light has been arranged to defeat itself. When a gravitational wave passes through, this careful balance is disturbed. The wave does not shove the mirrors in the usual sense. Instead, it gently stretches space along one arm and compresses it along the other, then reverses over and over in a pattern set by the distant event that produced it. One beam suddenly finds that its path is a tiny bit longer than before, while the other finds its path a tiny bit shorter. They are still racing down the same arms, still bouncing between the same mirrors, but the stage beneath them has shifted. When they reunite at the beam splitter, their rhythms no longer line up exactly as they did. The cancellation is incomplete. A small amount of light leaks through to the photodiode, bright enough for the electronics to notice, yet still dim by everyday standards. In that flicker, patterned in time, the gravitational wave leaves its signature. If the world were perfectly still, this would be the whole story. But LIGO lives on Earth, a restless planet. The ground trembles very slightly as oceans move and as wind presses on the land. Distant traffic, local storms, even someone closing a door in the wrong place can send vibrations through the building. On top of that are subtler sources, the random thermal jiggling of atoms in the mirrors and their supports, tiny electrical fluctuations, the faint whisper of any remaining gas. All of these disturbances can shift the mirrors by amounts far larger than the shifts caused by gravitational waves, threatening to bury the signal in noise. To quiet the instrument, the mirrors at the ends of LIGO's arms are made massive and smooth. Each one weighs around 40 kilograms and is polished so carefully that its surface errors are smaller than a wavelength of light. They do not sit rigidly on mounts that would pass along every shake of the Earth. Instead, they hang from silica fibers, which themselves hang from other stages of suspension, forming a kind of delicate, layered pendulum. This hanging system filters out many kinds of vibration, allowing the mirrors to move as freely as possible only in the directions that matter for the measurement. The vacuum system is pushed to extremes as well. The air is pumped out until the pressure inside the arms drops to about 1/1,000,000th of atmospheric pressure. In that near emptiness, stray molecules are so rare that a photon can travel for long distances without meeting one. The chance that a random puff of gas will shove a mirror or scatter a bit of light becomes vanishingly small. Even with heavy mirrors and deep vacuum, there is another kind of noise that cannot be cleared away with bolts or pumps. At very small scales, the world follows the rules of quantum mechanics. Light behaves not just as a smooth wave, but as a stream of tiny packets of energy, photons that arrive with a certain built-in randomness. Sometimes a few more arrive in a given moment, sometimes a few fewer. Their timing and number cannot be predicted perfectly, no matter how good the laser. This fundamental uncertainty shows up as a flicker in the light's phase and its brightness, a subtle graininess that places a limit on how quiet any optical measurement can become. For an instrument as sensitive as LIGO, this quantum graininess begins to matter. The random fluctuations can blur the very interference pattern that scientists are watching so closely. Rather than accept this as an unchangeable barrier, the designers use a technique with a gentle name. They squeeze the light. By sending the laser beam through an additional optical cavity, another carefully arranged set of mirrors and paths, they reshape the quantum noise, reducing it in the particular aspect the interferometer cares about most, and shifting the excess into another aspect that matters less. You can think of it a bit like tidying a room when you don't have time to sort every object. Clothes and books are scattered across the floor, making it hard to move. You can't make them vanish, but you can pick most of them up and stack them in one corner. The room isn't perfect, but the path you need is clearer. Squeezed light is similar. Quantum randomness can't be removed, but it can be gathered and shifted into a part of the light that the interferometer doesn't watch so closely. The fluctuations in the phase of the light, the exact timing of its wave crests, are calmed, while fluctuations in overall brightness are allowed to grow. Because LIGO reads phase with exquisite precision and cares less about tiny changes in brightness, this trade lets the useful part of the signal stand out more cleanly. Even with all this care, the instrument is never completely silent. There is always some hum, some flicker, some residual motion in the mirrors and the light. The goal is not to force the noise to zero, that would be impossible, but to make sure that when a real gravitational wave passes through, its pattern rises clearly above the remaining murmur. This balance is what people mean by signal-to-noise ratio. Improving it is like lifting a whisper just enough that it can be heard in a quiet room. Bit by bit, through heavier mirrors, deeper vacuums, better suspensions, and gentle tricks with quantum noise, LIGO has raised that whisper until events from distant corners of the cosmos can be traced in the data. And when the first of those whispers finally stood out beyond doubt, it was given a simple, almost plain name: GW150914. The letters mark it as a gravitational wave, the numbers as a date, September 14th, 2015. But behind that catalog label is a story that began 1.66 billion years ago, when two black holes far from our galaxy started to fall toward each other in earnest. Each was the collapsed core of a massive star, one about 29 times the mass of our Sun, the other about 36, orbiting together in the dark and slowly losing energy as they stirred the fabric of space-time around them. As they drew closer, their orbit quickened. What began as a slow dance became a tight spiral, each black hole tugging on the other, both dragging the surrounding space-time into their whirl. In the final moments, they were circling many times a second. Then, in less than a heartbeat, about 20 thousandths of a second, they merged. In that instant, a burst of gravitational energy rushed outward, a final shout from the collision. Trying to picture the power in that shout is almost beyond feeling. For that brief instant, the energy carried away in gravitational waves is thought to have outshone the combined light of every star in the observable universe by a factor of around 50. All the suns in all the galaxies shining together would have been dimmer than this one invisible event. Read as a bare fact, it looks like just another large number. Sit with it for a moment, and it becomes something stranger. The universe pouring unimaginable energy into a single, silent ripple of its own fabric. Those ripples then began their long journey. For 1.66 billion years, they crossed the widening universe, weakening as they spread, passing through gas clouds, galaxies, and the empty stretches in between. By the time they reached Earth and brushed past LIGO, the disturbance they carried was so faint that it hardly seems possible it could be measured at all. On a 4-kilometer arm, the passing wave changed the length by about 1,000th of the width of a proton. Not 1,000th of a millimeter, 1,000th of a proton, itself already far smaller than an atom. Numbers like that can slip through the mind without leaving much behind, so it helps to use a different image. Imagine the distance between Earth and Proxima Centauri, the nearest star beyond the Sun, over 4 light-years of empty space. Now, imagine changing that distance by about the width of a human hair. That is the scale of change LIGO was able to notice in its own arms. And GW 150914 was only the beginning. 3 months later, in December of the same year, LIGO picked up a second signal from another black hole merger, this one about 1.4 billion light-years away. During its first observing runs, as the detectors were tuned and improved, more and more of these chirps appeared in the data. Each one was a separate pair of black holes, heavy, invisible, locked in orbit until they collided and sent their final waves outward. Over its initial 3 runs, LIGO and its partners recorded more than 80 such mergers, turning what had once been a single miraculous detection into a growing catalog of events. Among all those signals, one in particular stands out with a different kind of beauty. In August 2017, LIGO and its European partner Virgo detected a wave pattern unlike the typical heavy black hole collisions. This one, labeled GW 170817, came from the merger of 2 neutron stars, ultra-dense remnants of exploded suns. The gravitational wave signal alone told scientists that the colliding objects were lighter than black holes but far more compact than ordinary stars. Because the detectors could locate the patch of sky where the signal originated, telescopes around the world turned toward that region. Dozens of observatories, using many kinds of light, from gamma rays and X-rays to visible and infrared, joined the search. Before long, they found a new point of light in a distant galaxy, the glowing aftermath of the neutron star collision. For the first time, an event in the universe was seen in both gravitational waves and electromagnetic radiation. Spacetime's ripples and photons glow, telling the same story together. This is what astronomers call multi-messenger astronomy. Gravitational waves were no longer just a quiet test of theory, they became part of a chorus. From that one event, scientists learned more about how heavy elements like gold and platinum are forged, how fast the universe is expanding, and what happens when the densest known stars in nature finally collide. After those first years of discoveries, the LIGO observatories went quiet for a while, not because curiosity faded, but because the instruments needed to grow more sensitive. Inside the vacuum chambers and control rooms, mirrors are replaced with more reflective ones. Suspensions are redesigned to isolate them better from tremors, and the systems that squeeze the light are refined to ease down quantum uncertainty. It is like teaching the detector to listen more intently, to separate the faint cosmic murmur from the remaining rustle of its own internal noise. By May of 2023, after roughly 3 years of this careful work, LIGO began its 4th observing run with better sensitivity than ever before. The same stretches of desert and forest now housed instruments that could hear weaker signals and probe a larger volume of the universe. And this time, LIGO was not listening alone. A new observatory in Japan, called Kagra, had joined the network. While LIGO's arms reach across the surface of the Earth, Kagra hides underground in the mountains near Hida, shielded by rock from much of the surface vibration that plagues other sites. And it cools its mirrors to cryogenic temperatures, so their atoms jiggle less. During an engineering run in May, Before the observing campaign had fully settled into its stride, the joint network picked up a signal that may have come from a neutron star being swallowed by a black hole. Some of these candidate detections will need time to analyze and confirm. The process is careful by design. Scientists cross-check the data, compare it with models, and rule out earthly disturbances that might mimic a cosmic wave. But if the early hints from this fourth run are any sign, the coming years will bring a steady stream of new events. Black hole mergers of many masses, neutron-star collisions, and perhaps combinations we have never recorded before. While the current observatories listen, plans for the future are quietly taking shape. In India, a new detector, often called LIGO India, is being developed as a collaboration with the existing teams. When it comes online, it will join LIGO in the United States and Virgo in Europe, along with Kagra in Japan, to form a wider global network. With more detectors spaced around the Earth, triangulating the origin of a signal becomes much more precise, shrinking the patch of sky where astronomers must look for accompanying flashes of light. Further ahead, upgrades with names like LIGO Voyager are being designed. Voyager aims to push sensitivity even deeper by using heavier mirrors, more advanced suspensions, and lasers operating at different wavelengths. Heavier mirrors move less in response to the same tiny forces, and new laser frequencies offer fresh ways to calm quantum noise. Beyond Voyager lies the dream of third-generation observatories, facilities like Cosmic Explorer, with arms tens of kilometers long instead of 4. With interferometers, size truly matters. The longer the arms, the more a passing gravitational wave will change their effective length, and the easier it becomes to distinguish that change from noise. And then there is the proposal that feels like the natural next step after listening from Earth, carrying the interferometer into space itself. The Laser Interferometer Space Antenna, usually called LISA, would not be anchored to the ground at all. Instead, it would consist of 3 spacecraft flying in a triangular formation, separated by millions of kilometers. Laser beams would travel back and forth between them, forming an enormous interferometer stretched across the emptiness. With arms on that scale, LISA would be sensitive to a different band of gravitational waves, tuned to lower frequencies that arise from more massive and more widely separated systems, and even more exotic theoretical sources. Gravitational waves already serve as a bridge between different kinds of astronomy. They offer direct evidence of remote and ancient phenomena that are invisible or nearly invisible to telescopes working only with light. At the same time, they complement those telescopes. When an event like GW170817 is seen in both gravitational waves and in light, each messenger fills in part of the picture. The waves describe the motion of mass, the timing and structure of the collision itself. The photons reveal the hot aftermath, the jets and glowing debris and chemical fingerprints. As more detections accumulate, this partnership between light and gravity will sharpen our sense of how the universe has evolved, how fast it is expanding, how often certain kinds of stars are born, collide, and fade. As detectors on the ground and in space grow more sensitive, they may begin to pick up not just individual events, but a background, a faint, persistent rumble made from the overlapping waves of countless distant sources. Thinking about a background like that naturally brings to mind another ancient signal, the cosmic microwave background, a soft, nearly uniform glow of microwave light that fills the sky. It is the afterglow of the hot, dense state we call the Big Bang. Its discovery transformed cosmology, anchoring the idea that the universe began in a hot, expanding phase. Yet even that light can only take us so far back. It was released when the universe was already about 380,000 years old, cooled just enough for atoms to form and for photons to finally travel freely. If we want to listen to earlier times, when everything was still so dense and turbulent that light could not move without being scattered, we need a different messenger. Gravitational waves, because they slip so easily through matter, could have crossed those first moments almost untouched. Somewhere in spacetime, there may be a background of primordial waves carrying imprints from fractions of a second after the beginning. Listening for that background is one of the quiet, profound goals of gravitational wave astronomy. It feels a little like slowly tuning an instrument, bringing an indistinct hiss into focus, hoping that beneath the noise there is a faint, ancient hum, a record of the universe finding its shape. With each improvement in sensitivity, each new observatory, and each carefully analyzed signal, we take a small step toward hearing how it all began. And recently, a hint of that hum may have brushed against our instruments in an unexpected way. In 2023, a group of astronomers working together under the name Nanograv announced evidence that they might be starting to hear a long, low background murmur, not a sharp chirp from a single collision, like the event's LIGO records, but a slow vibration woven through the universe itself. To find it, they didn't rely on lasers in tunnels. Instead, they used stars scattered across our galaxy as timing beacons, turning pulsars into the distant endpoints of a detector that stretches for tens of thousands of light years. The stars they chose are not ordinary. They are pulsars, collapsed stellar cores, dense and small, spinning hundreds of times each second. Many of them sweep beams of radio waves through space like cosmic lighthouses. When one of those beams crosses Earth, our radio telescopes pick up a pulse, a tiny flash of radio light, arriving again and again with astonishing regularity. Some pulsars keep time more steadily than the best atomic clocks we can build. For astronomers, each one is a natural metronome, ticking away in the darkness. If space-time between us and a pulsar were perfectly calm, those ticks would arrive as predictably as the beat of a well-tuned drum. But if a gravitational wave passes between us and the pulsar, it very slightly stretches or squeezes the distance the pulses must travel. Because light is fast but not instantaneous, that change in distance shows up as a small advance or delay in the arrival times of the pulses. One wave might make pulses from a given pulsar come a little early for a while, then a little late, sketching a gentle pattern in time. The effect on any one pulsar is tiny, easily drowned out by other sources of noise. But the Nanograv collaboration uses many pulsars at once, spread across the sky. When a background of very low-frequency gravitational waves washes through the galaxy, it does not affect each line of sight in isolation. It imprints a particular set of correlations in the timing of pulses from all of them. By patiently collecting data for years and studying how these small irregularities correlate from one pulsar to another, astronomers can look for the signature of that common background, a faint rise and fall in space-time itself. To see why these waves are so different from the ones LIGO hears, it helps to think for a moment about frequency. Sound can be high or low. A violin string sings in thousands of vibrations per second, while a distant storm rumbles only a few times per second or less. Light, too, has a range of frequencies, from high-energy gamma rays to slow radio waves. Gravitational waves are no different in that way. They come in many pitches, each corresponding to how quickly the source is changing its shape or motion. LIGO and its sibling detectors are tuned to hear the higher notes in this cosmic song. They are most sensitive to waves from binaries, pairs of black holes or neutron stars that are already in a tight embrace, whipping around each other dozens or hundreds of times a second just before merging. In those final moments, the frequency of the gravitational waves climbs into a band that laser interferometers can detect, and the event shows up as a brief, rising chirp. Far earlier in the lives of those same binaries, when the objects are still far apart and orbiting each other more slowly, the waves they emit are much lower in frequency. The ripples are stretched out in time, their peaks passing perhaps only once every months or years. The energy is still there, but it is spread over longer intervals, like a deep organ note compared to a sharp piano key. LIGO's design makes it practically deaf to these very slow undulations. Its arms and control systems are optimized for faster vibrations, and the lowest notes simply slip past unnoticed. Now imagine not just one binary, but many. Throughout the universe, galaxies host massive black holes at their centers. When two galaxies merge, drawn together by gravity over millions or billions of years, their stars rarely collide. The spaces between them are so vast that most simply pass by, but their overall gravities interact. The orbits of stars are shuffled, gas clouds are stirred and compressed, and, at each galaxy's core, the supermassive black holes are brought into one another's neighborhood. Those central black holes, each millions or billions of times the mass of the Sun, can become a bound pair, a supermassive binary. At first, they orbit at great distances, swinging slowly around a common center. Over very long timescales, they may spiral closer, losing energy to their surroundings and to the gravitational waves they emit. Each such pair contributes its own soft, low-frequency signal to the universe. Because the orbits are slow, the waves are ultra-long, with frequencies in the nanohertz range, a crest and trough taking years to pass. If you could translate those frequencies into sound your ears understand, they would correspond to pitches far, far below what humans can hear. Our ears top out at low tens of hertz. A nanohertz is a billionth of a cycle per second, a rhythm so slow it feels more like a slow tide than a tone. For an interferometer like LIGO, those waves are effectively static. They change too slowly to register. But over years of watching pulsars, the accumulated shifts in pulse arrival times can reveal them. The universe does not host only one such supermassive binary. Over cosmic history, galaxies have merged many times. Each merger may leave behind a pair of central black holes, which then slowly tighten their orbit. Some of those pairs may eventually coalesce. Others may still be in an earlier, leisurely dance. Their collective gravitational waves overlap and blend, just as the chatter of many voices becomes a steady murmur in a crowded room. The result is not a single, sharp signal, but a background, a persistent hum of ultra-low frequency gravitational waves pervading space. It is this background that pulsar timing arrays like Nanograv are beginning to glimpse. For more than a decade, they have pointed radio telescopes at carefully chosen pulsars, recording the arrival times of millions of pulses. Tiny deviations in those times, on the order of tens to hundreds of nanoseconds, are compared across the sky. If the irregularities were caused only by clock errors on Earth or by quirks in the pulsars themselves, they would not show a coherent pattern from one direction to another. But if a gravitational wave background is present, the timing deviations should be correlated in a specific way depending on the angles between pairs of pulsars. In 2023, the collaboration reported evidence for just such a pattern, a statistical hint that the pulses we receive are being nudged together by a common, slowly changing distortion of spacetime. The signal is not yet as crisp as a single event, like GW150914, but it has the flavor of a chorus rather than a solo. Many supermassive binaries, scattered over billions of light years and billions of years, may be singing at once, their long, low notes summing into one pervasive background. If that interpretation is correct, it opens a new window on the growth of structure in the universe. By studying the strength and shape of the background hum, astronomers can infer how often galaxies of different sizes have merged, how rapidly their central black holes have grown, and how these processes have changed over cosmic time. The background becomes a kind of census, taken in the language of gravity rather than light. But there is another, even more tantalizing possibility woven into this story. The ultra-low frequency gravitational wave background we hear today may carry not only the voices of merging black holes, but faint echoes from much earlier times. Some theories of the very early universe predict that processes shortly after the Big Bang, such as violent phase transitions, or the snapping and shaking of hypothetical objects called cosmic strings, could have generated gravitational waves on a grand scale. As the universe expanded and cooled, those primordial waves would have stretched, their frequencies drifting downward into the same nanohertz range that pulsar timing arrays are now probing. Disentangling these different contributions is not simple. The background from pairs of supermassive black holes is expected to be strong, perhaps the main swell in the signal. Any more exotic ripples from the very early universe may be smaller, delicate patterns riding quietly on top. Yet even the possibility that we are starting to touch that realm is profound. With light, our view is walled off at the cosmic microwave background, the point in time beyond which the universe was too dense and hot for photons to travel freely. With gravitational waves, we have a chance to lean past that wall a little, using the fabric of space-time itself as the thing that carries information to us. So, when astronomers talk about a faint hum detected with pulsars, they mean more than a clever technical trick. They are pointing to the first hints of a background that may have been ringing through the cosmos for almost as long as there has been a cosmos to ring. Each carefully logged pulse arrival, each line in a timing table or point on a correlation graph, is like laying a fingertip against that deep vibration and feeling, dimly but honestly, the slow music of the universe's history. To feel how special that is, it helps to remember what we usually mean by the universe's earliest light. Most of the time, that phrase refers to the cosmic microwave background, a soft, nearly uniform glow that fills the sky in every direction. You won't see it with your eyes on a clear night, but sensitive radio instruments reveal it as a gentle bath of microwave radiation. That glow comes from a time when the universe was just a few 100,000 years old. Before then, all the way back to the first instant, the cosmos was so hot and bright and full of charged particles that any light trying to cross it was scattered again and again. In that sense, everything earlier than the microwave background is hidden behind its own brilliance. Gravitational waves, slipping almost unhindered through those first moments, may be our way of listening to what happened there, even when no light from that era can ever reach us. To say that the young universe was opaque to light is to say that photons could not travel very far without being stopped and scattered. In those first moments and minutes and thousands of years, everything was incredibly hot and dense. The matter that would one day become stars and planets did not exist as calm atoms. Instead, it was a wild sea of charged particles, free electrons and bare protons, racing around with so much energy that they could not settle down and bind together. Physicists call this state of matter a plasma. It is the same kind of stuff we see today in the hearts of stars and in lightning. But back then, it was not confined to a tiny region. The entire universe glowed with it. In a place filled with plasma, light is never left alone. Photons try to move, but everywhere they go, they bump into charged particles. Each collision can absorb the photon and then emit a new one in a different direction. Step by step, the light is forced to zigzag, changing its path again and again. Instead of traveling cleanly across space, it is trapped, like someone trying to make progress through a crowded room and being jostled at every turn. On large scales, this means that no clear beam can cross the young universe. The light and matter are locked together, sharing the same hot, restless motion. As the universe expanded, it slowly began to cool. Expansion does that. It stretches not only space, but the energy in the things inside it. Over hundreds of thousands of years, the temperature dropped from nearly unimaginable values to something gentler. Eventually, it became cool enough that electrons and protons could finally combine and stay combined, forming neutral atoms of hydrogen and helium. Once that happened, a quiet transformation took place. Neutral atoms do not scatter light the way free charges do. Suddenly, photons were no longer stopped at every step. They were free to travel vast distances without constant interruption. The moment when this shift happened is sometimes called recombination, and the release of light that followed is what we now observe as the cosmic microwave background. At the time, that light was more like a bright orange-white glow, similar in temperature to the surface of a very hot star. But as the universe continued to expand over billions of years, the wavelengths of those photons were stretched. Their color slid down the spectrum, from visible light to infrared, and finally into the microwave range. Today, that ancient flash has cooled into a faint, uniform background at only a few degrees above absolute zero. This is why the cosmic microwave background is often described as the earliest light we can see. It is not the first thing that ever happened, but it is the oldest electromagnetic signal that has been able to cross the universe to us without being scattered beyond recognition. Light from before that time cannot reach us directly because it never had a chance to travel freely. It was trapped in the plasma, constantly exchanged with matter, losing any clear memory of the specific events that produced it. Gravitational waves live by different rules. They are not made of photons at all. They are ripples in space-time itself, tiny stretches and squeezes in the distances between things. Because they are not charged and do not carry electrical interactions in the way light does, the early plasma barely notices them. To gravitational waves, that opaque young universe is almost completely transparent. They could have moved through it as easily as ocean swells pass beneath a cloud of mist. That means that while light can only show us back to the time of recombination, gravitational waves have the potential to carry information from much earlier moments, from times when the universe was only fractions of a second old, any violent processes happening, then phase transitions in the fields that fill space, the motion or breaking of hypothetical cosmic strings. The birth and inflation of spacetime itself could have launched waves that have been traveling ever since. These are what we call primordial gravitational waves, signals born in the universe's first breath. Over the billions of years that followed, the universe has stretched by a tremendous factor. Just as this expansion lengthened the wavelengths of the photons from the cosmic microwave background, It also stretched the wavelengths of primordial gravitational waves. Even if they began at relatively high frequencies, the ongoing expansion would have slowed their rhythm, pulling their crests farther apart in time. Today, many of those ancient waves would be expected to show up at ultra-low frequencies, with periods measured not in fractions of a second, but in years and decades. Those ultra-slow waves share the same band of the spectrum as the ones produced by pairs of supermassive black holes slowly orbiting each other in distant galaxies. Different sources, different stories, but overlapping pitches. All of them together make up what astronomers call a stochastic gravitational wave background. Not a single sharp signal, but a wash of many contributions layered on top of one another. Some arise from galaxy mergers and black hole binaries. Others, we hope, may carry whispers from the first instance after the Big Bang. Recovering this mixed background is like trying to make sense of the sound in a crowded cafe. Individual voices are hard to separate, but the overall murmur still tells you that many conversations are happening, and with enough careful listening you might begin to pick out patterns. For gravitational waves, listening means finding ways to measure how space-time itself is bobbing and bending under the influence of these ultra-long ripples. The first idea many people have is simple enough. If LIGO can detect high-frequency waves with 4-kilometer arms, why not build a bigger LIGO for the low ones? Make the arms longer, spread them farther apart, and we should be able to see slower, larger waves. In spirit, this is correct. An interferometer detects changes in distance along its arms, and the size of those changes depends on how the wave's wavelength compares to the arm length. Very long waves are easier to recognize if your measuring stick is also long. But when we run the numbers, the dream of an earthbound, ultra-low frequency interferometer begins to drift out of reach. The relationship between a wave's frequency and its wavelength is simple. The wavelength is equal to the speed of the wave divided by its frequency. Gravitational waves travel at the speed of light, about 300 million meters per second. For the nanohertz waves, that pulsar timing arrays are sensitive to waves that complete just one full cycle in 1 billion seconds. That speed divided by frequency gives a wavelength on the order of 10-17 meters. That figure is hard to picture, so it helps to anchor it with familiar scales. The average distance between Earth and the Sun, one astronomical unit, is about 10-11 meters. A single light year, the distance light travels in a year, is about 10-16 meters. A wavelength of 10-17 meters is therefore not just larger than our solar system, it spans roughly 10 light years, comparable to the distance to some of our nearer stellar neighbors. It is a ripple so vast that it rolls across whole regions of the galaxy at once. To really feel the shape of such a wave, an interferometer would need arms that stretch over a significant fraction of that wavelength. 4 kilometers is a tiny scratch on its surface, too small to show the gentle up and down clearly. Even if we could somehow lay tunnels along continents, across oceans, wrapping the arms almost all the way around the Earth, the planet itself would still be far too small. Earth's diameter is only about 7 meters, 10 million meters, which is 10,000 times shorter than a typical nanohertz gravitational wave wavelength. There are also practical limits that arrive long before we reach even that point. Building vacuum tunnels hundreds or thousands of kilometers long on the surface of a living, shifting planet would be an engineering challenge beyond anything we have attempted. The ground moves, the air shifts, Weather and tectonics and human activity all conspire to jostle and rumble the structure. No amount of mirror polishing or vibration isolation could fully tame such an enormous, fragile machine in such a noisy environment. So while the basic idea of a bigger LIGO is appealing, it cannot be our path to the ultra-low frequency universe. For those waves, we have to be more imaginative. We have to use measuring sticks that are already long enough, ones that nature has placed for us. The distances between Earth and distant pulsars, the wide triangular formations of spacecraft spread through space. Ground-based interferometers remain perfect for catching the quick, sharp notes of stellar mass black holes and neutron stars as they collide. But for the long, slow swells with wavelengths of tens of light years, we need detectors that match their scale, listening patiently over years to the way our planet itself drifts up and down in the cosmic tide. Even with that vast, imaginary interferometer stretched across the galaxy, there is still the problem of scale. The waves we are trying to sense are so slow and so broad that no construction project, no ring of tunnels on Earth, or even in the wider solar system could match them. The wavelengths we want to feel run for tens of light years. Our entire planetary neighborhood is just a small knot along their length. If we insisted on building a physical detector to span them, we would have to wait for a future civilization able to anchor instruments between the stars. Instead of waiting for that distant day, astronomers found a way to use what the universe has already placed around us. They turned to pulsars, the ultra-dense, rapidly spinning neutron stars we talked about earlier, and treated them as the fixed points of a detector that is already big enough. Each pulsar is the collapsed remnant of a massive star, squeezed into a sphere only a few tens of kilometers across, yet carrying more mass than our Sunday. As it spins, it sends beams of radio waves streaming out from its magnetic poles. If one of those beams happens to sweep across Earth, we see a pulse of radio light every time the star completes a rotation. For some pulsars, that rotation is astonishingly stable. They spin hundreds of times each second, and their pulses reach us with such regular rhythm that they can rival the best atomic clocks humans have built. Over years of observation, the arrival times of their pulses can be predicted to within millionths or even billionths of a second. That steadiness turns each pulsar into a kind of cosmic clock, ticking in the darkness, its beat crossing thousands of light years. If space-time between us and a pulsar were perfectly calm, we could write down a simple model for those arrival times, and they would follow it almost exactly. In reality, many small effects nudge them. Earth orbits the sun, wobbles on its axis, and is gently tugged by the gravity of other planets. The radio waves that leave the pulsar have to cross clouds of thin gas on their way to us, and that interstellar material can delay certain frequencies a little more than others, the way a piece of tinted glass slows and colors light passing through it. Astronomers account for as many of these influences as they can. They know Earth's orbit and rotation with exquisite precision and can subtract those motions from the data. They monitor the interstellar gas along each line of sight and model its changing effect on the pulses. After all of that careful correction, there are still small timing irregularities, leftover residuals, as the observers call them. At first glance, those residuals look like a kind of gentle noise, tiny advances and delays, seemingly random, a scatter of points around a smooth prediction. The idea behind Nanograv and other pulsar timing arrays is that hidden inside that scatter, there may be a pattern. If only one pulsar were being timed, it would be almost impossible to disentangle the subtle fingerprint of a gravitational wave background from all the other sources of jitter. But Nanograv does not listen to just one. Over the years, its members have carefully selected a set of especially steady pulsars and watched them together, turning them into a single, shared instrument. This curated collection is called a pulsar timing array, a constellation not of ordinary stars, but of clocks. For Nanograv's latest results, the array consists of 68 millisecond pulsars, objects that spin so quickly that each one completes a rotation in just a few thousandths of a second. They are scattered all across the sky, some above the plane of our galaxy, some within it. Their distribution is deliberate. By having clocks in many directions, astronomers can sense how any large-scale distortion of spacetime affects different lines of sight. Millisecond pulsars are chosen because their pulses are particularly regular over long periods. The faster they spin, the more stable their rhythm tends to be, like a finely balanced gyroscope, humming steadily once it has been set going. Over months and years, their pulses keep time with a regularity that rivals the best laboratory clocks. They are, in many ways, the timekeepers we always wished we could place at the far edges of a detector arm, quietly reporting back everything they experience. With such an array in place, the method becomes one of patience and statistics. Radio telescopes on Earth, some large single dishes, some networks of smaller antennas point toward these pulsars again and again, collecting their pulses and writing down the exact time each one arrives. As the years pass, these logs grow into long records. For each pulsar, astronomers compare the observed arrival times with the times predicted by their best models of motion and interstellar delays, and they note the residuals, tiny differences that remain unexplained. Some of those residuals are caused by local quirks. A bit of extra gas drifting into the line of sight can delay the pulses in a way that affects only that one pulsar. A subtle change in the pulsar's own spin can alter its rhythm for reasons that have nothing to do with gravitational waves. But gravitational waves, especially those in a background made from many sources, act more like a slow change in the stage beneath all the musicians at once. A single, vast wave crossing the galaxy stretches space a little more in some directions and squeezes it in others. Pulses from two pulsars separated by some angle on the sky will therefore be nudged in related ways, sharing a pattern of advances and delays. It is in those shared patterns, correlations between the timing residuals of different pulsars, that the signature of the gravitational wave background is expected to appear. To look for it, astronomers consider all possible pairs of pulsars in their array. For each pair, they ask, as time goes by, do the residuals of these two clocks tend to drift together or in opposite ways? Then, they plot how strong that correlation is against the angle separating the pulsars on the sky. If there were no gravitational wave background at all, only individual sources of noise, the points on that plot would scatter around zero. Some pairs would show a bit of correlation by chance, others a bit of anti-correlation, but overall, there would be no clear structure, just a cloud. However, the presence of a gravitational wave background should imprint a specific curve on this plot, a gentle rise and fall that depends only on the angle between pulsars. This pattern was first worked out by two physicists, Hellings and Downs, and now bears their names. According to their calculation, pulsar pairs that are close together on the sky should show a certain level of shared timing shifts, while pairs separated by larger angles should show different levels, and pairs at right angles should tend to be affected in almost opposing ways. When you draw that relationship as a curve, it has a distinctive shape, like a soft wave. For years, pulsar timing arrays have been expanding their catalogs, refining their models, and improving their sensitivity, all in the hope of seeing that curve emerge. On June 28, 2023, the Nanograv collaboration announced that, after more than 15 years of observations of their 68 pulsars, the first strong hints of the Hellingsdowns curve had appeared in their data. When they plotted correlation against angle, the points did not sit flat along zero. They traced, within their uncertainties, the expected pattern of shared stretching and squeezing. Because the measurements are so delicate, each point on that graph carries an error bar, a vertical line showing how much uncertainty remains. Yet, taken together, the pattern is hard to dismiss. The team estimated the statistical significance of their result at around 3 sigma, which is a way of saying there is only about a 1 in 1,000 chance that the observed correlations are just a coincidence of random fluctuations. In particle physics and cosmology, the community often asks for 5 sigma, roughly a 1 in a million chance of a fluke, before calling something a formal discovery. By that standard, the gravitational wave background is not yet officially confirmed. But 3 sigma is still strong, especially when similar hints are beginning to appear from other pulsar timing arrays, observing different sets of pulsars with different telescopes. It is like hearing a distant melody, not just once, but echoed from several rooms at once. As more data are collected, the error bars will shrink. Each additional year of timing extends the length of the records, making it easier to see the slow sway of nanohertz waves. New pulsars may be added to the array, improving the coverage of the sky and providing more pairs to compare. Better models of the interstellar medium and the pulsars themselves will help peel away local noise, leaving the common signal more exposed. If the pattern truly comes from a background of gravitational waves, its outline will grow sharper with time, its significance creeping closer to that 5 sigma threshold. Even now, before every detail is settled, the emerging curve already whispers secrets. We cannot yet point to a specific feature and say, that is this black hole binary, or to another and say, there is a trace of the universe's first second. The background we have glimpsed is still a blended choir, not a set of isolated voices, but its overall loudness and shape can begin to tell us how many supermassive black hole pairs are out there, how massive they tend to be, and how quickly they are merging as galaxies collide and grow. In the years ahead, by combining pulsar timing data with other observations of galaxy populations, of active galactic nuclei, of the regions around central black holes, astronomers hope to untangle more of the story, separating the nearby from the far, the recent from the ancient. Some parts of the hum may be traced to the restless centers of galaxies. Other parts may hint at physics that goes beyond our current understanding, reaching back toward the conditions that prevailed in the first instance after the Big Bang. For now, the picture is simple and quietly beautiful. Across the Milky Way, dozens of millisecond pulsars spin and shine, each one a lighthouse sending out pulses into the dark. On Earth, dishes of metal and arrays of antennas turn their faces to the sky, catching those pulses as they arrive. In hard drives and notebooks, the times are written down, compared, corrected, and compared again. Out of that long patience, a pattern gradually appears, a hint that our entire galaxy, and we along with it, are gently bobbing in a vast, low-frequency sea of spacetime. We cannot feel the motion in our bones, but through these distant clocks we can watch the tide. Every so often, tucked between the usual flares and flickers of the night sky, astronomers have begun to notice something that feels almost like a cosmic camera flash. Since 2018, about once a year, a sudden blue blaze has appeared where there was nothing recognizable before, swelling into extreme brightness and then fading away again. Each one is so luminous that a normal supernova beside it would look like a candle held up against a floodlight. Some of these flares have been relatively nearby in cosmic terms, a few 100 million light years away. Others have come from the deep distance of billions of light years. They resemble one another enough to be members of the same strange family, yet no one can say with confidence what kind of engine is buried at their hearts. As more of them were noticed and tracked, astronomers began to realize that they were dealing with a new category of event. The pattern emerged slowly, like a shape gradually picked out in dim light. Each time a telescope happened to catch one of these transients early, observatories all over the world would hurry to point their instruments at it, gathering measurements in as many colors and wavelengths as possible before it slipped away. With every new example, the list of shared traits grew longer, and the theories about their origin grew more intricate. And yet, now and then, the data would twist just far enough out of expectation to leave even seasoned researchers quietly shaking their heads. These events were eventually given a name that sounds almost clinical: luminous, fast blue optical transients, usually shortened to the softer-sounding LFBOTs. The words are descriptive rather than poetic. Luminous, because they are extraordinarily bright in visible light. Fast, because they brighten and fade on a timescale of hours or days, instead of the weeks and months we associate with most supernovae. Blue, because when we spread their light out into a spectrum, the peak falls at shorter wavelengths, corresponding to very high temperatures. Optical transients, because they come and go in visible light, appearing briefly and then sinking back into the background glow. For now, LF bots are mysterious, in part because the sample is so small. The first one was spotted only in 2018, and since then, we have only managed to catch a handful of others in enough detail to study them properly. The sky is big, the events are brief, and telescopes can only watch so much at once. That makes every single detection precious. With so few examples, it is hard to write a strict definition that does not risk leaving something important out. Still, there are a few characteristics that most researchers agree on. LF bots shine strongly in blue optical light and are also bright at higher energies in ultraviolet, X-rays, and often in radio waves as well. They rise quickly, as if switched on, and then fade just as quickly, sometimes dropping in brightness by large factors over only a few days. If you think of a typical core collapse supernova, the kind that signals the death of a massive star, the pattern is a little different. In those explosions, the star tears itself apart, its outer layers thrown into space in a great expanding shell. Light from the blast grows over days to weeks, reaches a peak, and then declines over months as the debris cools and as radioactive elements created in the explosion decay away. LFBOTs echo this general sense of flash, then fade, but they do it on fast forward and with the brightness turned up dramatically. It is as if someone has taken the familiar supernova story and compressed it into a much shorter, fiercer episode. Because they are so brief, catching LFBOTs at all requires a special kind of watching. One of the instruments that helped reveal the first of them is NASA's ATLAS system, a network of telescopes designed primarily as an early warning for asteroids that might come too close to Earth. One of these telescopes, the Atlas facility at Haleakala in Hawaii, spends its nights scanning the sky over and over, mapping changes and looking for moving points of light. On June 16, 2018, during one of those routine surveys, Atlas recorded something that did not fit the usual patterns: a sudden, intense point of light that blazed up to a brilliance about 100 times that of an ordinary supernova, and then began to dim within days. News of that odd flash spread quickly through the astronomical community. When something strange appears, there is often a kind of quiet scramble. Observatories in different time zones trade messages, plan follow-up observations, and adjust their schedules to catch the fading event before it is gone. In this case, telescopes on the ground and in space were turned toward the patch of sky where the flash had occurred. Careful analysis traced its origin to a galaxy in the direction of the constellation Hercules, roughly 180 million light-years away, a neighbor by cosmic standards, close enough that details could be studied with some clarity. The transient was given an official catalog name, AT2018 Cal, according to the usual naming conventions. The last 3 letters, Cal, were just an accident of the system, but they were too charming to ignore. Astronomers, who often spend their nights in quiet control rooms, are not immune to a bit of affection. Before long, everyone was simply calling the event the Cow. Underneath the nickname, though, lay something stubbornly difficult to classify. At first, the Cow was filed under a familiar category, a Type Ib supernova. Those are core collapse explosions in which a massive star has already shed most of its hydrogen envelope, leaving a stripped-down core that finally gives way under its own gravity. In a Type Ib, the collapsing core rebounds and drives a shock wave outward, blowing off the remaining layers and lighting up the surroundings. The early brightness and rough shape of the Cow's light curve seemed, at a glance, to put it in that family. But spectra, the fingerprints of light, when it is split into its component colors, began to tell a more complicated story. When scientists examined the Cow's spectrum closely, it did not look quite like a textbook Type IB. The emission lines, which map out the presence and motion of different elements, were unusually broad, suggesting material moving at very high velocities. At the same time, the helium lines, which should have been prominent in a typical Type IB, were unexpectedly weak. That combination pushed some researchers to think of another subtype, a Type IC-BL supernova, where BL stands for broad-lined. These are energetic explosions thought to be linked, in some cases, to the birth of black holes and to gamma-ray bursts. For a while, it seemed plausible that the Cow might fit there instead. Even that reclassification did not sit entirely comfortably. The more astronomers pored over the data, comparing the Cow to known supernovae, examining its light curve from the first rise to the late-time glow, tracing its behavior across X-ray, optical, and radio wavelengths, the more it resisted any neat label. Certain pieces looked familiar, but the overall picture felt like something new. Ordinary supernovae take their time, ramping up to full brightness. The Cow went from almost nothing to enormous luminosity in just a few days. Where most supernovae are content to shine at a level we now recognize as normal, this event outpaced them by factors of 10 to 100. The geometry of the explosion seemed odd, too. In the simplest sketches, a core collapse supernova is roughly spherical. Material is blown outward in all directions. Reality is messier, and we now know that strong magnetic fields, rotation, and internal instabilities can distort the blast, making some regions denser or faster than others. Even so, when observers reconstructed the cow's outflow, they found signs that it was far from gently lopsided. Some described it as the most spherical explosion they had ever studied, as if the energy had been channeled more like a focused outburst or jet than a smooth, expanding shell. All of this left theorists with a puzzle. What kind of engine could produce such a bright, fast, oddly shaped event? Ideas began to circulate. One suggestion was that the cow might not be a standard supernova at all, but rather the aftermath of a star being torn apart by a nearby black hole, a tidal disruption event where a passing star strays too close and is shredded, its gas spiraling inward and releasing huge amounts of energy. Another possibility was that it was indeed a supernova, but one in which the collapsing core had immediately formed a compact central object, a newborn black hole or neutron star, whose intense radiation and winds then powered the extraordinary luminosity and strange geometry. In the years since, more LF-bots have been spotted, each one given its own catalog name and often its own friendly nickname. Each new member of the family brings both reassurance and fresh confusion. Reassurance because their similarities confirm that the cow was not a one-off accident. Confusion because subtle differences between them hint that there may be more than one pathway to such an explosion. For now, they remain among the brightest and most bewildering flashes the universe has shown us. Brief blue beacons reminding us how much of the sky's story is still being written in unknown ink. It is tempting, when something strange appears once, to treat it as a curiosity and move on. The mind quietly files it away under odd, but probably a fluke. When it appears twice, doubt softens but does not quite let go. Two examples might still be coincidence. It is only when the same kind of thing shows up a third time, in a new place, under new conditions, that a pattern begins to feel real. Astronomers are no different. With only the cow to puzzle over, they had little to lean on. They could test ideas, build models, argue back and forth, but without other examples, every conclusion felt a little like guessing in the dark. They did not have to wait long. Only a few months after the cow's 2018 debut, the sky produced another brief, brilliant blue flare with similar properties. Then, in 2020, a third event followed. Each had its own long, official catalog designation, strings of letters and numbers encoding when and where it was first seen, but the last three letters again offered more playful labels. Keeping up the tradition, astronomers began referring to these newcomers as the koala and the camel. Quietly, almost without fanfare, a tiny zodiac of LF-bots was born. The cow, the koala, the camel. Three separate explosions in different corners of the universe, all flashing fast, blue, and bright. With three in hand, researchers could finally start doing what they love most: comparing. They studied the light curves, the spectra, the radio afterglow, the X-ray behavior. They traced each event back to its host galaxy and tried to understand its surroundings. One of the first patterns that rose from this careful work had less to do with the details of the light and more to do with where, exactly, these explosions were happening. In every case, the blast did not come from the quiet outskirts of a galaxy or from the halo of old stars around it. Instead, each one was traced to a location within a spiral arm, a bright, curving lane of gas and young stars winding around the galaxy's center. Even though the cow, the koala, and the camel lived in very different galaxies, at very different distances from us, all three seemed to be nestled in these spiral arms. That may sound like a small detail, but for astronomers, it was a strong hint. The spiral arms of galaxies are busy places, full of cold gas clouds where new stars are born. The most massive of those newborn stars burn hot and bright but live briefly, using up their fuel in only a few million years before collapsing and exploding as core collapse supernovae. Because their lives are so short, they do not wander far from their birthplaces. Their deaths tend to happen close to the clusters where they formed, which in turn tend to live in the spiral arms. If LFBOTs were some unusual form of core collapse supernova, this is exactly where you would expect to find them, sitting in the arms, near regions of active star formation, among other young, massive stars. The host environments of the cow, koala, and camel seemed to fit this picture neatly. For a while, this emboldened the idea that, underneath all their oddities, these flashes were still, at heart, stellar deaths, of a kind perhaps extreme, perhaps aspherical, perhaps powered by newborn compact objects, but still linked to the familiar story of massive stars collapsing under their own gravity. Then the sky, with its usual disregard for our comfort, offered another surprise. Like Atlas in Hawaii, the Zwicky Transient Facility in California uses a wide-field camera to scan the northern sky over and over, every couple of nights, looking for anything that changes. It is a bit like taking repeated photographs of a crowded room and asking a computer to point out anything that has moved or brightened. In 2022, among the many ordinary flares and variable stars, this survey picked up another LFBOT-like explosion. Its first flash looked familiar, very bright, very blue, rising quickly against the darkness. But after that initial burst, the newcomer refused to behave like its predecessors. Instead of flaring once and then sliding steadily downward, its light curve became restless. Short, intense bursts kept appearing long after the original flash should have faded away. Each mini outburst was only minutes long, yet many were nearly as bright as the first. The event was eventually given a formal name, but it also inherited an animal nickname that matched its twitchy, unpredictable behavior: the Tasmanian Devil. The energy involved was staggering. Integrated over time, those repeated pulses emitted more energy than hundreds of billions of suns like ours radiate in the same interval. Yet they were squeezed into a series of brief, staccato flashes, as if some engine at the heart of the explosion were turning on and off again and again in rapid succession. To astronomers watching the data come in, it looked almost like a star dying, flaring, dimming, and then somehow being driven back into activity multiple times in a row. Whenever something this unusual appears, cautious minds immediately turn to the possibility of error. Could the instrument have glitched? Was there a calibration problem with the camera? Could some subtle issue in the data pipeline have created the illusion of repeated bursts where there were none? Science has seen its share of apparent breakthroughs that evaporated under closer inspection, undone by a loose cable, a software bug, or a misapplied formula. Healthy skepticism is not just allowed, it is necessary. In this case, that skepticism was met with a reassuring answer. The Tasmanian Devil did not exist only in the data of a single telescope. Observatories around the world, 14 of them in all, turned their instruments toward the source and saw the same behavior. They watched the light flicker and surge, counted at least 14 distinct pulses, and suspected that the true number was higher still. with some bursts missed in the gaps between observations. Together, these independent measurements painted a consistent picture. The strange, pulsing light was really there. Despite how bizarre it seemed, the Tasmanian Devil did not immediately rule out a supernova-related origin. Some models of stellar collapse include central engines, a newborn neutron star, or black hole surrounded by dense debris that can, under the right conditions, feed energy back into the expanding material in fits and starts. Even though the rapid rebrightenings were unexpected, they did not obviously contradict the broad idea that LFBOTs might be extreme kinds of core collapse explosions. If anything, they hinted that watching these events in real time might offer a rare, continuous glimpse into how a star's death unfolds from the inside out, rather than inferring it from static snapshots of different objects at different stages. And then, just as the pieces seemed on the verge of falling into a slightly more comfortable arrangement, another LFBOT arrived that pushed them apart again. On April 10, 2023, astronomers detected yet another big, fast, blue transient. In many ways, it looked like a sibling of the earlier members of the LFBOT family. Its brightness, its color, the shape of its light curve all aligned closely with what had been seen in the cow, the koala, the camel, and the Tasmanian Devil's first flash. But when researchers traced its position back to its surroundings, they were met with a shock. This new event, soon nicknamed the Finch, was not nestled in a spiral arm. It was not even in the disk of a galaxy at all. Instead, it flared up in the thin, dim space between galaxies, about 3 billion light-years from us, and roughly 15,000 light-years from the nearest large galaxy. On the sky, it sat in what looked like the middle of nowhere, the quiet region between two galactic systems, rather than the bright lanes within them. For the leading theory, this was a serious blow. Massive stars, the kind that undergo core collapse, are born from dense clouds of gas. Those clouds live in galaxies, particularly in their arms and central regions, where gravity and turbulence bring material together. Between galaxies, space is almost unimaginably sparse. A few lone stars may be kicked out into those intergalactic reaches by gravitational encounters, but the environment there does not favor the birth of new, short-lived giants. If LFBOTs truly required fresh, massive stars collapsing in place, it was hard to see how such an event could occur so far from any obvious nursery. The Finch seemed to embody all the hallmarks of an LFBOT, yet it had chosen a home utterly unlike those of its predecessors. In a single stroke, it reminded astronomers that the universe is not obliged to keep its mysteries neatly boxed. Just when a pattern begins to feel secure, a new example steps forward from the dark and tilts the whole picture sideways again, inviting everyone to look closer, think more softly, and accept that, for now, some of the brightest lights in the sky come from stories we are only just beginning to learn how to tell. Faced with the Finch glowing in the emptiness between galaxies, astronomers had to quietly admit that their neat picture had cracked. If these outbursts really were just exotic deaths of massive young stars, why would one of them go off so far from any obvious cradle of star formation? It was like finding a fresh campfire in the middle of a frozen lake with no wood in sight. Something in the story was missing, and their ideas had to open up again. Two main possibilities rose to the surface as ways to explain how the Finch could flare where it did. Neither is proven, both come with gaps, but each threads the known facts into a different shape. One leans on a kind of black hole we have long suspected but never firmly seen. The other imagines two neutron stars spiraling together in the dark, merging in one of the most powerful stellar explosions we know how to describe. The first idea begins with the notion of an intermediate mass black hole. We already know two ends of the black hole family well. At the small end are stellar mass black holes, the remains of heavy stars that have collapsed, with up to a few dozen times the mass of our Sunday. At the other extreme sit supermassive black holes, millions or billions of solar masses, anchoring the centers of galaxies. Between them lies a missing middle, black holes with roughly 100 to 10,000 times the Sun's mass. On paper, these middleweights make a lot of sense. They could be seeds that later grew into supermassive giants, or products of dense star clusters slowly merging their contents. Yet despite years of searching, their existence has never been pinned down beyond doubt. A few candidates flicker in X-ray data and in the motions of nearby stars, but the evidence has always stayed a little slippery. If an intermediate mass black hole were quietly lurking in the outskirts of a galaxy, or in the space between galaxies, it could act as a kind of cosmic predator. Simulations suggest that stars can become bound to such a black hole and loop around it several times, perhaps 5 very close orbits, before being flung away. Each time the star sweeps in, the black hole's tidal pull tugs harder on the near side than the far side, peeling off material. With every pass, the star grows more ragged, losing mass into a stretched stream of gas. In the end, only a compact core and long, thin tails of debris may remain. Part of that gas spirals inward, heating as it falls and shining fiercely. Part of it is hurled outward at tremendous speeds, up to about 1/10 of the speed of light. Seen from far away, the whole episode could appear as a sudden, very bright flash that fades quickly, a light show with energies and velocities similar to what we infer for LFBOTs. In that sense, the Finch's speed and brilliance sit comfortably beside the idea of a star being torn apart, bit by bit, by a medium-sized black hole. Where might such black holes live, if they really exist? One plausible hiding place is in globular clusters, dense, roughly spherical swarms of old stars that orbit in the outer halos of galaxies. A galactic halo is a faint envelope of stars, dark matter, and clusters that surrounds the brighter disk and bulge. In a spiral galaxy like our Milky Way, it stretches far beyond the glowing band we see on dark nights. Globular clusters drift within this halo, like compact knots of starlight, each holding hundreds of thousands of stars in a region only a few tens of light years across. Their cores are crowded enough that stars can pass close to one another, and over billions of years those encounters can trigger mergers and cause massive stars and remnants to sink toward the center. Some simulations suggest that in such an environment, an intermediate mass black hole could form at the cluster's heart. If the Finch happened to lie inside or just beside such a cluster, too faint and distant to stand out in our current images, then its middle-of-nowhere location would not be so lonely after all. The explosion could have been the end of a star trapped in repeated close orbits around an unseen middleweight black hole, stripped on each passage until a final outburst flung its remains outward. In that picture, the Finch becomes not just another strange flash, but a possible signpost to a long-sought population of hidden black holes. The second idea takes us along a different path. Instead of a star and a black hole, it imagines two neutron stars, ultra-dense stellar remnants caught in a slow gravitational dance. Neutron stars cram more than the Sun's mass into a ball only about 20 kilometers wide. When two of them form a pair, They can orbit each other for millions or billions of years, gradually losing energy to gravitational waves and spiraling closer. As their separation shrinks, their orbits speed up. Just before they touch, they may circle one another hundreds of times each second. When they finally collide and merge, the result is what we call a kilonova, a brilliant flash powered by the formation of heavy elements in the ejected matter and by the behavior of the merged core. Kilonovae spray out material rich in gold, platinum, and other heavy nuclei, and they shine across the spectrum, from gamma rays to infrared. We have already seen one such merger in detail. Its light, accompanied by a gravitational wave signal that traced the tightening orbit in the last seconds. That gravitational wave chirp is one of the signatures of a neutron star merger. A rising tone in the data of detectors like LIGO and Virgo, reflecting the increasing frequency of the waves as the orbit tightens. If the Finch were a kilonova, born from two neutron stars, coalescing in the quiet between galaxies, we would expect such a chirp to have washed across Earth at the same time as its light reached us. Catching it would have offered strong support for this picture. But timing, in this case, was unkind. When the Finch exploded in April 2023, LIGO was temporarily offline, undergoing upgrades and maintenance before its next observing run. Virgo, its European partner, was also not delivering data at the needed sensitivity. With the detectors quiet, no gravitational wave record exists for that moment. If a neutron star chirp did pass by, it slipped past unheard. Astronomers also checked for a burst of gamma rays, a short, high-energy flash, often associated with some kilonovae when narrow jets form and point toward us. For the Finch, no clear gamma ray burst was seen. That could be counted as a mark against the neutron star idea, but it is not decisive. The event happened about 3 billion light-years away. Any gamma ray signal could easily have faded below our instrument's sensitivity, or the jet might simply have been pointed elsewhere, like a flashlight aimed just past our shoulder. All of this leaves the neutron star scenario hovering in a gray area. The Finch's brightness and timescale do not rule out a kilonova, especially one with an unusual geometry. Yet without gravitational wave data, and with no obvious gamma-ray partner, we are left with a sketch that might be accurate or might be missing some crucial strokes. For the people trying to understand these flashes, it is a quietly uncomfortable place to stand. On one hand, they are witnessing something rare and powerful, a category of event that has only recently entered astronomy's vocabulary. On the other, some of the most telling clues arrived while important detectors were being serviced. Still, that unease is less a dead end and more an invitation. While the Finch's gravitational waves, if any, are lost to us, other kinds of evidence may still be gathered. One plan, already taking shape, is to use the James Webb Space Telescope, with its sharp infrared vision, to take deep images of the region where the Finch appeared. Webb is sensitive enough to pick up very faint, distant objects that older telescopes might have missed, including tiny globular clusters shining weakly in a galaxy's halo. If Webb reveals a faint cluster of stars at the Finch's position, it would lend weight to the intermediate mass black hole idea. A cluster is exactly the sort of environment where such a black hole might form and wait for an unlucky star to drift close. If, instead, Webb sees only emptiness, theorists may have to bend their models again or imagine other, stranger engines. In parallel, other teams are focusing on the simplest path forward, finding more of these events. So far, only a handful of luminous, fast blue optical transients, the cow, koala, camel, Tasmanian devil, finch, and a few cousins have been studied closely. Each one adds a piece to the puzzle, but most of the picture is still blank. To learn how common they are, how varied, and what environments they truly prefer, astronomers need a much larger sample. The way to build that sample is to keep sweeping large parts of the sky, night after night, with wide field surveys. Instruments like Atlas in Hawaii and the Zwicky Transient Facility in California already do this for the northern sky, catching brief flashes as they appear. On the horizon is the Vera C. Rubin Observatory in Chile. Once fully operational, Rubin's survey camera will scan the entire southern sky every few nights, gathering far more light than previous facilities and turning up huge numbers of changing objects. In that flow of images, events like LF bots should stand out as sudden blue spikes. Automated software will flag candidates, and then space telescopes such as Hubble and JWST, along with large ground-based observatories, can be steered to watch them fade, split their light into spectra, and search for X-ray and radio counterparts. Each new LFBOT discovered this way will be another quiet clue, another angle on the engines that power them. For now, these explosions are still young in our understanding. They do not yet have a settled place in textbooks, and even their basic nature is uncertain. The Finch, lighting up a stretch of space between galaxies, has raised more questions than it has answered. Are we seeing one phenomenon with many faces, shaped by its surroundings, or several different kinds of events that just happen to look alike from far away? Are intermediate mass black holes quietly revealing themselves through these flashes, or are neutron star mergers playing a role we did not expect? In the pauses between detections, those questions hang in the background, like faint constellations waiting to be traced. Somewhere out there, more luminous fast blue optical transients are already preparing to ignite. When they do, and when our instruments are looking the right way at the right time, a few more pieces of the pattern will fall into place. Until then, the brightest blue flares keep a part of their story to themselves, and we, watching from our small world, learn to sit with the mix of wonder and not knowing they leave behind. The more closely we watch these bright blue explosions, the more they slip out of any neat box we try to place them in. Each new LFBOT feels like a message written in a language we are only beginning to recognize. A flash of light, a handful of spectra, a fading afterglow across radio and X-rays. We line the clues up carefully, and they still refuse to spell out a simple story. For now, the only honest thing to say is that we do not yet know what they are. We only know that they are real, and that the universe is trying something interesting where they appear. That uncertainty can feel a little restless, especially when the phenomena are so dramatic, but in a way, we are standing in a very old posture. For hundreds of generations, people have looked up at odd lights in the sky and waited for patterns to emerge. The tools have changed from naked eyes to glass lenses, from photographic plates to digital arrays and space telescopes, but the rhythm is the same. You point your instruments at the darkness, you keep watch, and you let time add detail to the picture. Bit by bit, the sky that once seemed full of one-off wonders begins to reveal its deeper habits, and things that once looked like isolated miracles slowly take their place in a wider, quieter order. Gravitational waves are a good reminder of how that patience can be rewarded. Back in 1916, when Albert Einstein first worked through the equations of general relativity, he realized that massive objects in motion should send ripples through space-time. The idea was as strange then as it sounds now. Not waves in water or air, but waves in the very distances between things. If two heavy bodies orbit each other or collide, the curvature of spacetime should respond, sending out expanding rings of stretching and squeezing that travel at the speed of light. On paper, it was a natural consequence of the theory. In practice, Einstein doubted anyone would ever be able to measure such a tiny disturbance. He treated it almost like a whisper his equations were making, beautiful, but likely to remain unheard. You can picture those waves by returning to something simple. Imagine throwing a stone into a still pond. Circles spread outward from the point of impact, growing larger and fainter as they travel. Gravitational waves are like those circles, but the pond they move across is space itself. As a wave passes, it makes the distance between 2 points grow a little, then shrink a little, without leaving any lasting mark. For two objects 4 kilometers apart, the change might be smaller than a fraction of a proton's width, far below anything our senses can notice. For a long time, that seemed like the end of the dream. The universe might be full of these ripples, but they would always remain just beyond our reach. But a century is a long time in human technology. Quietly, over decades, ideas for how to feel those ripples were turned into prototypes, then into serious instruments. Today, there is a small family of gravitational wave observatories spread around the world. In the United States, there are the twin LIGO detectors. In Europe, Virgo. In Japan, Kagra. Soon, others will join. They do not look like traditional telescopes. There are no domes or lenses aimed at the stars. Instead, each site is a kind of giant listening device, 2 long, straight tunnels at right angles, with powerful lasers and exquisitely suspended mirrors at their ends, all tuned to notice when space-time itself shivers. The way they work is both subtle and playful. A laser is split into 2 beams and sent down the perpendicular arms. There, the light bounces back and forth between mirrors, traveling many times up and down each tunnel before returning to the place where it began. When space-time is calm, the distances along the 2 arms stay fixed, and the beams recombine in a way that very nearly cancels the light out. The detector sits in an artificial darkness of its own making. When a gravitational wave passes through, one arm is ever so slightly stretched while the other is slightly squeezed. That difference, tiny as it is, makes the beams fall out of perfect step, and a little burst of light appears where there should have been almost none. No single observatory listens alone. Because the Earth is round and restless, and because local noise can masquerade as signal, the detectors share their data, compare notes, and check one another's whispers. A wave sweeping through our planet will reach one site a fraction of a second before another. By measuring those tiny delays and the differences in loudness from place to place, scientists can work out roughly where on the sky the wave came from, like tracing the source of a sound heard by several microphones scattered across a room. When everything lines up, when LIGO, Virgo, Kagra, and their partners all see the same pattern at nearly the same time, it becomes very hard to argue that the universe was not speaking. The changes those instruments track are unbelievably small, equivalent to changing the distance between Earth and the nearest star beyond the Sun by the width of a human hair. Yet the lasers and electronics are sensitive enough to follow them. The raw data looks like a faint squiggle in time. But when scientists process it and, if they wish, shift it into the range of human hearing, each event turns into a short, rising sound. A chirp that climbs in pitch as 2 massive objects spiral together more and more quickly. Lighter black holes produce longer, lower-pitched calls, Heavier ones rush together faster, their chirp quick and high. In just a few tenths of a second, an entire cosmic collision can be heard as a brief brushstroke of sound, a soft whoop that carries the memory of something unimaginably violent very far away. Since the first detection in 2015, that global network has recorded dozens and then hundreds of such murmurs. Some come from pairs of black holes, dark against any telescope's eye, but loud in gravity. Others come from neutron stars, their merger lighting up the sky in gamma rays and visible light, as well as in waves of space-time. A few may be mixed pairs, a black hole pulling in a neutron star and swallowing it. Each new signal adds a dot to our map of how often these events happen, how heavy the colliding objects are, and how the universe has stitched its structures together over time. What began as a fragile, one-off measurement has slowly become a new way of doing astronomy, one that does not care whether the sources shine in ordinary light at all. It is impossible to say exactly which flashes or waveforms will do the same for luminous, fast blue optical transients. Somewhere in the stream of future data, there may be an LF bot that happens close enough, in a clean enough environment, with the right combination of gravitational waves, X-rays, radio echoes, and deep follow-up imaging, that the pieces finally lock together. Maybe we will catch one in the act of forming a newborn black hole or neutron star. Maybe we will see clear signs of a star being torn open by a hidden intermediate mass black hole, or the unmistakable pattern of a distant kilonova. Maybe the answer will be something we do not yet have a name for, a new kind of engine quietly at work in the dark. Until then, the work looks deceptively simple from the outside. Telescopes sweep the sky, night after night. Software combs through the images for new points of light and sudden changes. When a candidate pops up a fast, blue flare where there was emptiness before, alerts ripple out to observatories on mountaintops and in orbit. They turn, they watch, they collect every photon they can before the transient fades. Later, in quiet offices and late-night video calls, teams sift through the data, test models, argue gently, and write down what they think the universe is trying to say. Months or years after the actual flash, its afterimage still lives in graphs and equations, in shared folders and draft papers, slowly being translated into understanding. There is a kind of comfort in knowing that we are part of that long, patient chain. The same human curiosity that once wondered about wandering guest stars in ancient Chinese records now listens to the tiny tremor of space-time and the brief blaze of LF bots at the edge of observation. We are not the first to land in the middle of a mystery, and we will not be the last. Some questions close in a few years, others take decades. A few may always remain a little out of reach, like distant lights, slightly blurred by the atmosphere. Living with that mix of clarity and uncertainty is part of the work and part of the quiet joy. If you carry anything with you from this wander through gravitational waves and bright blue transients, let it be this: the universe is full of signals we are only just beginning to notice. Some arrive as a soft hum in pulsar timing data, some as a sudden chirp in a laser interferometer, some as an unexplained flash on a wide-field camera's nightly survey. Others drift toward us as ancient microwaves from the cosmic background, or as subtle changes in the motions of stars. We are learning, slowly and together, how to turn those signals into stories about how things form, change, collide, and begin again. Out beyond the line of city lights, the sky still looks calm to the naked eye. But tucked inside that calm are black holes merging, neutron stars colliding, galaxies shaping one another, and, every so often, a bright blue flare, whose cause we have not yet pinned down. Our role, small and steady, is to keep watching, keep listening, and keep letting our questions stretch just a little farther than our current answers. Somewhere in that stretch between what we know and what we do not yet understand is the space where discovery lives, waiting patiently for us to arrive. And if you happen to be listening on a quiet night, letting your thoughts drift as the world settles, it is a gentle thing to remember that above you, the universe is always in motion, writing new stories in waves and light, and that, in our own small way, we are learning to read them.